Assignment 2 is being returned today. I'm told by Rebecca that the grade distribution is not the same as for assignment 1. Apparently assignment 2 was more difficult for some people, quite a few people. So the grade is, in assignment 1 many people received very high grades. Assignment 2 has a heavier tail. So it's a good opportunity to say something about grading. As you know from the website, the grade is more or less a third the assignments, a third the midterm, and a third the final. I have a lot to say about the grading system in America. I have some concerns about it, but the way I usually assign the grade is not by I first combine all of the numerical grades into a weighted average. Now I have a weighted average. Now how do you convert it into letters? There's some arbitrariness in that. What I typically do is I have a preconceived notion of what I consider a passing level of understanding. And I look at the exams and the homework to get a sense of where that passing level of understanding, where this threshold that I feel comfortable saying you passed the class. And usually the vast majority of students are past that, but it's at the tail end where I might say, well, I cannot in good faith say that this person passed the class. Once I decide on that, that for me is the breaking point for a failing grade. Then there's a borderline performance. That would define the D grade. And then from then on, I look at natural clustering of the average, the weighted average, and decide on the breaking points for the A, B, and C. I suspect that many other people do the same thing, but I don't know if they discuss that with you. So why am I saying all of that? Because if you have a grade in an assignment that is not very high, that doesn't mean any one grade in an assignment is very hard to correlate to whether it's a passing grade or a C or a B or an A. It is, however, useful for you to take your grade and compare it to the grade distribution in the class for that assignment or for that midterm or for that final. And for this we will give you the histograms for how everybody else has performed. So any one assignment has a very, very small impact on the grade. What's more important is that the assignment might serve as a indicator for you of whether you understand the material or not, and that in my mind is more important. So if you got a grade that's lower than you thought, or even if you didn't, look at the solutions, make sure you understand the solutions, make sure you understand wherever you did make a mistake, what the mistake was and what the answer is now. If you feel comfortable after that process that if you had to take the assignment again, you will do very well, or the midterm or the final. That's a very good sign. Now the process is not completely blind. I do allow myself to be influenced, usually in the positive direction, by participation, by any other interaction I have with the students that shows me that they understand the material. Any questions? Okay. We're going to talk about neural networks today. As usual, I'll start with where we're coming from, what our motivation is. But at some point, we're going to do with neural networks what we did with decision trees, which is just evaluate them along the criteria that I outlined before. Do you remember 3 questions you need to ask? Representation power, thank you. First question is representation power. Second question was search. How do you find members of this class that agree with the training data? And third one, which is kind of tied to the second, maybe second and third are the same. I'm sorry? Generalization and learning. So they're not the same. Search is more of a computational issue. Generalization has more to do with your choice of soft bias and hard bias. So when you choose a whole class like decision trees or neural networks, really formally what you're choosing is a hard bias first. A representation, which means a representation bias, hard bias. But implied in that would be a whole slew of algorithms and heuristics that introduce a soft bias. So in the case of decision trees, the soft bias of the standard ID3 algorithm is towards a small tree, small number of nodes. Towards the end of the last lecture, I mentioned to you that you can replace that bias with other related but different biases, taking into account the cost of asking certain questions, for example. Or you may want, for some reason, to introduce a bias towards shallow trees as opposed to small trees. Small trees have very few nodes. Shallow trees have very short paths. So a tree that implements an end of n variables, the way we did it in class is by introducing one long branch further down. And that has a linear number of nodes, but is very imbalanced and has also a linear depth, which is not a great kind of depth to have. You prefer to have a logarithmic depth. So maybe for implementation reasons or for any other reason, you may prefer other properties. Or because you may believe that the answer, the true answer, lies in a set of solutions that have some other property. So the point is, the class, like decision tree, strictly speaking, is only about hard bias representation. Then the algorithms that you use and the way you choose a tree based on the data introduces a soft bias. And a soft bias has every bit of an impact on generalization as hard bias does. And then in parallel to the soft bias, there's the question of whatever soft bias introduced, how do you go about finding a solution that is based on that soft bias? And that's a computational question. That's the search question. So the soft bias and the search go hand in hand. Okay, so we're talking about neural networks, and the motivation of neural networks comes from our brains. We talked a little about it at the beginning. It's kind of stuff that gets me very excited, so I can talk about it for hours. But I want to remind you of some properties of neural networks, of real neural networks in the brain. First, let me tell you a little bit about what is known about the brain at a very superficial level. I'm sure many of you know a lot more than this. But our brains are made of neurons. Do you know how many? Anybody?
100 billion.
100 billion. That's 10 to the 11, right? Yeah, that's about right. 10 to the 10 to 10 to the 11. Neurons. Neurons are connected to each other via synapses. Synapses are bridges between neurons, communication channels between neurons. How many synapses are there in the brain? Anybody wants to guess? Any biology major or minors here? Ten to the 14th to 10 to the 15th synapses. That's roughly 10 to the 4 synapses per neuron. So if you think about the connectivity pattern, the connectivity statistics, every neuron is connected on average to about 10,000 other neurons. And similarly, every neuron receives on average about 10,000 connections from 10,000 other neurons. That's an average. Some neurons are great listeners and some neurons are great shouters. You know, some neurons talk to a lot but don't receive much input from others, and vice versa. This is an overall average. What do neurons look like? Schematically, they have well, neurons are cells, and cells have very diverse shapes, and even neurons, there are many different types of neural cells, but schematically there is something called an axon, and there are dendrites here. please don't take my drawing too seriously. I don't know how to draw. But there's an area that's sort of diffused that can go pretty far out, and into which all the 10,000 on average other messages come in. And they come in different places. Some of them come in at the end of it, some of them come in closer to here. So they arrive from everywhere. And as these messages, which are electric messages, arrive, they cause an electric signal to start building up. And when enough of them arrive, they pass a certain threshold. And this is very important also for computational reasons. It is not a linear process. It is not the case that the more messages come in, the more neurons that are connected in send messages, the more the current neuron sends its own message. It is a very non-linear process. There is a threshold. As long as, if I'm a neuron and I receive messages from 10,000 other neurons, as long as the total sum of the messages is below my threshold, I don't do anything. I just absorb it in some way. But once it passes the threshold, it causes me to fire. So there's a clear non-linear threshold. And when the threshold is passed, there's a wave, an electric wave that goes through the axon and goes out, connects to everybody else that this neuron is connected to. It is actually not a clock-driven process the way a computer is, in the sense that every step, every clock tick, you have a chance of doing that. It's a continuous process, which means if there are lots of neurons that are connected to me that are constantly sending me electric signals, I will be constantly excited and send signals out, and the more they send me, the faster the rate at which I send my own signal. Up to a point. Due to limitations of how the system is implemented in terms of collecting ions and recovering molecules from the environment and all of that, I cannot fire faster than 1,000 times a second. So my peak firing rate is 1,000 shots or 1,000 pulses per second. I'll write it down. It is also called the neuron switching time. We call it 0.001 second. So peak firing rate is 1,000 per second. There is a tremendous amount of debate and uncertainty in the computational community about how are signals encoded. Where is information here? Is information in the rate of firing? This is the commonly held belief that the rate at which the neuron fires is what conveys information. In that case, every neuron conveys one continuous variable. The continuous variable is the rate of firing, with some limited resolution of the continuous variable, but it still can be thought of as continuous. Or is it a binary thing that every millisecond, either it fires or it doesn't? This is less likely. It's a very noisy system with lots of continuous properties. Another very intriguing theory is that information is conveyed not so much in the rate of firing, but actually in the synchrony of firing between different neurons. So if two neurons fire in synchrony, neurons are involved in the same process, that conveys information. And if they're off phase, that conveys different information. We know that the brain does amazing things, but we don't really understand the underlying computational mechanism. We don't even understand what the fundamental unit of information is. Is it the synchrony of the message? Is it the rate of the message? Is it something else? Now we can think of the neuron, of the brain as an input-output machine. Inputs come from our senses. They get converted into electric signals that feed into some of the neurons, and then these neurons feed into other neurons, and those feed into other neurons, and eventually they feed into effector mechanisms. That means into ways of doing things, moving muscles, typically. You can roughly divide this kind of machine into processing the input, making a decision, and executing the output. But the boundaries inside the brain are not very clear. There's a fair amount known about the first part, the processing of the input. For example, visual cortex, the best studied part of the system. We know that we get photons hitting our retina in the eye, and that there are cells sitting in the back of the retina, and they're photosensitive. So they see light in different positions, and they fire. These are neuron cells. And once they fire, their message goes, along with millions of others, along an optic path into the visual cortex, which is actually in the back of our head. And the visual cortex is a piece of the brain that has its own internal structure. There's something called V1 and V2 and V3, and then V2A and V2B. And there's a fair amount known about the sort of signal processing aspect of how this matrix of light gets transformed into detection of edges, detections of areas, detections of edges, detection of orientation, all the way up to detection of what's called 2.5D images, which is some representation between 2D and 3D. After that, it all gets lost in the mess of the brain, and we don't really know what happens after that. And then there's a cognitive part where you actually think about what you experience or what you perceived. And then there's a decision part. If you remember my task of pushing a button when you see your grandmother, it is an example of how all the parts of the brain, the three parts of perception, cognition, and decision, and action, operate. The signal goes through your retina, through your visual cortex. From there, neurons project to many other parts of your brain. Somewhere, it must interact with stored memories, because you have a stored memory of your grandmother, maybe more than one. We believe that the hippocampus, which is a little part of the brain even lower than the visual cortex right here, is where long-term memories are stored. There's a lot of work on how they're stored and how so much memory can be stored in such a small place, and the different properties of this storage. There's good reason to believe it's distributed. It's sort of smeared, that every memory, every representation is smeared over a large part of the brain, rather than sitting in one particular location. Incidentally, do you guys know about RAID? Redundant arrays of disks? Computer scientists, you don't know the brain, but you know RAID. So RAID has discovered recently what the brain has known all along, which is distributed representations are safer, because damage tends to be localized. So if you damage a tiny part of the brain, all of your images or memories are going to be slightly distorted, and if they have any redundancy to them, they can be reconstructed, which is exactly what RAID is about. Disks tend to fail locally. If you smear your data across many disks and introduce some redundancy, you can reconstruct any local damage. So going back to your grandmother, we have the perceptual part. It goes through your visual cortex, then it goes through some kind of a decision mechanism that interacts with memory. And once you decide, yeah, that's grandma, you have to decide to push a button. And once that decision is made, somehow the neurons that innervate your finger get triggered. And even that process is incredibly complicated, because it's not just your finger. There's a lot more that goes into it. You have to provide pressure, support from this part. Otherwise, it's just a finger. You don't push a button like this. You push a button like this, right? Your entire hand is involved. It's probably dozens of muscles, and each muscle is innervated by a large number of neurons. So it's a very complicated process. And it's all done by a combination of these guys that I don't even know how to draw, that basically take lots of inputs and make a discrete decision on whether to fire or not, and if they do fire, they're heard by lots of other neurons. And now the most amazing part is the grandmother recognition time, which I told you about, which is 0.1 of a second. In the slides they call it scene recognition time, because it's the time it takes you to recognize most scenes. But I like the example of grandma. It's very concrete. So, grandma recognition time And that's from the moment the picture is projected until you push the button. Is 0.1 second, which, given the peak firing rate of 1,000 times per second, means that any one neuron in your brain only had a chance to fire at most 100 times. Now, if you think of this combination of neurons as performing some kind of computation, the computation is done in massively parallel hardware, which is massively connected, but it's done in very short parallel time, but short time, namely 100 time steps. And that to me is absolutely amazing, that you're able to do something so complicated with 100 time steps, where each time step, the kind of operation you perform is computationally very simple. You add up the input that comes into you as a neuron, and you decide to fire or not to fire. True, you're not the only one doing it. There are up to 10 to the 11 others who do that too. But nonetheless, every step, every individual player in this game does something very simple, and after no more than 100 such steps, you have a complicated decision out, implemented into a plan of action and a set of muscle contractions and so forth. This is absolutely amazing to me. Now contrast that to the computer architecture. So modern computer architecture is also known as von Neumann architecture. Have you heard that term, von Neumann? So I'm not sure I got his name spelled out. Neumann. Maybe he spells it like this. Neumann. I'm not sure. I'm sorry. B-E-U. Is that right? So he's considered, in some sense, the father of modern computer architecture. There are lots of other fathers of computers and mothers. I mean it. Ada Lovelace and Turing and a few others. But he's in this century, not the century, the 20th century as opposed to the 19th century. He was the father of cybernetics, of the whole study of self-regulating systems. And he came up, or at least articulated and formulated the basic fundamentals of architecture of modern computers, which are that you have memory and you have a processing unit, and both your data and your instructions are stored in memory. And the basic operation of a computer is that you grab a piece of instruction, the next instruction, from memory, analyze it, use that to decide which pieces of data to grab from memory, perform some operation on them, and store the result back somewhere else. This is the essence of a von Neumann architecture, and this is what most modern computers do. Very, very different than the architecture of the brain. It is not inherently parallel. In fact, it is very sequential. One of the beauties of it is that data and code are treated the same. Code is viewed as data. It has fundamental, deep philosophical implications. It's what allows a tremendous amount of theoretical advance in computability and computational complexity and decidability. A lot of deep mathematical logic issues come from the fact that you can look at code as data, code and program as type of data. It has this duality of looking at it as bits or looking at it as have meaning. So very important stuff that came out of the von Neumann architecture. If you compare it to the brain, in the brain data and instructions are not the same. Data is the electric signals. What are the instructions? What is the program? Well, you can think of the program as the way the brain is wired, the way it's connected, who talks to whom, and how strongly they talk. I didn't actually mention that. I should mention that. When I said that there are synapses that connect two neurons, if you take this whole picture and you put it here as one neuron, and you put another neuron here, and let's say there's a synapse that connects them, that synapse has particular properties. You can think about it as maybe a bridge that could be narrow or wide. It allows the message to go through easily or less easily. So the impact of this neuron on this neuron is mediated by the strength of the connection between them, by the synapse. It could be a very strong connection, in which case activity here influences this a lot, or it could be a weak connection. And in fact, it could also be a negative connection. So synapses are fall into two different types. One is called excitatory. To excite, yeah. And inhibitory. Excitatory connection means that the more this fires, the more likely this is to fire. An inhibitory connection means that the more this fires, the more this is likely to not fire. And when this guy gets an inhibitory connection, we'll put a little minus sign here. And if this guy gets a lot of excitatory connections and some inhibitory connections, and remember it gets on average 10,000 of them, then the decision to fire or not to fire is made by summing up all the excitatory connections and then subtracting from them all the inhibitory connections. And remember that each excitatory and inhibitory connection is not counted, they're not all counted equally. Some of them have a stronger excitatory effect, some of them have a weaker excitatory effect, some of them have a stronger inhibitory effect, and so forth. So you can think about it as a weighted sum of both positive and negative terms. And if the total sum exceeds the threshold, we fire, otherwise we don't. So going back to the comparison with von Neumann, where is the program in the brain? You could say that the program is both in the topology of which neuron is connected to which other neuron, but also in the strength of the synapses. Which synapses are positive, which are negative, and how positive and how negative they are. This has been the accepted wisdom, and it still is the accepted wisdom, that the ability of the brain to perform computations is encoded in where the synapses are and in exactly their strength. Are they positive and negative, and how positive and how negative they are.
Don't they also change their strength though? I mean, it's not as though your brain is wired how it's wired and it stays that way. I thought that as you learn things.
Yes. Excellent point. So our brains are elastic and dynamic, and they learn to do things. How is learning manifested in the brain? The common belief is that it is manifested through changes in the strength of the synapses. For biological reasons, synapses cannot change from inhibitory to excitatory. So, but they can still change from being very inhibitory to less so, or very excitatory to less so or more so. So the strength of the connection can change, the sign of the connection does not change. It is generally believed that this is what learning consists of. Now there are animals out there who have brains that do not learn. I don't know if it's been correlated directly to ability or inability to change synapses. A much more difficult question is, even if we accept that our brains learn or change what they compute by changing the synapses, how do they know which synapses to change and in which direction? This is the learning problem. Okay? And there are some attempts to answer that, but we're still far away from answering it. There is very strong evidence that the synapses are really what's important, and it comes from the fact that we're born with far more synapses than we have as adults. You've all heard that we lose brain cells every day. That's true. I don't know, the number is 100,000 a day or something like that. But what you may not know is that we are born with a much, much larger number of synapses. In fact, when we're born, I don't know if it's true that all neurons are connected to all other neurons, but certainly the pattern of connectivity is much larger. And then while we're embryos, and then later in the first 2 months of life, something like 99% of our synapses die out. So what we're left with, okay, so they're not fully connected. That's ridiculous. You can't have 10 to the 11 times 10 to the 11. That would be way too much. But if you lose 99% of your synapses, that means you started with 10 to the 16, and you ended up with 10 to the 14. Only 1 in 100 synapses survive. Why are we born with so many if we're going to lose all of them? Well, a reasonable answer is that part of learning in the first few months of life is knowing which of these synapses to trim and which to leave. You can think about it as a sculptor who has this big block of some kind of stone and you chisel out the parts you don't need to reveal something meaningful inside. When you have so many synapses, there's not much meaning in there. There's just potential for carving out the meaning. And you need to get rid of these synapses in a meaningful way, in a judicious way, to leave those that leave meaningful paths of computation. Okay. We're going to work with representations like this one, where the circles are the neurons and the lines are the synapses. We take our motivation and our inspiration from the brain, but we're going to diverge from that pretty quickly. There are people who try to go back and learn more from the brain about how neural networks might be useful. But the main thing we get from it is an existence proof. If somebody had told you before you knew anything about the brain that you can build a machine, this big, let's say the brain of a mouse, that does not have any processors, any like Intel processors inside, but it just has a huge blob of very simple electronic components that just take lots of inputs and fire, and somehow that device can recognize a cat under any lighting conditions and any positions of occlusion and command an incredible array of muscles to turn around and run like mad and do a million other things that mice do that we can't get computers to do. Recognize cheese, smell cheese, whatever. That sounds unbelievable. How can this kind of architecture do such complicated stuff? But we know that it does. And it's an incredible inspiration to think, well, maybe the way von Neumann thought is not the best way to think about computation. Maybe there's something fundamental, a fundamentally different way of thinking of computation, of input-output mapping, that doesn't map into this grab an instruction, grab the data, perform something on it, send it back. Maybe there's something about this massive parallelism of very simple integrators that has the ability to compute things faster and better. It also brings up the question is at what level of description does the understanding of the brain lie for us? If you say, okay, people are incredibly good at recognizing grandmothers, is it because they have the hardware that a PC does not have, that they have this massively parallel thing? Or is this just a detail of biological implementation, just an accident of evolution, and really the interesting stuff happens at the higher level of description, how these things are combined together. And maybe there's a way of implementing it on a von Neumann machine that will be every bit as good, and it does not require neurons. In fact, there are people who believe that looking for the answer in the neurons is not appropriate, is not the right way to look for it. And they would say to you, if you want to understand how a modern computer like a PC works, and how it does all this wonderful Microsoft Word and PowerPoint and games and all of that, would you go into the computer and open the motherboard and look at the chip? You wouldn't say anything. Let's suppose you look at it with a microscope. You open a Intel processor and you look at the printed circuitry, and there's no way you can understand from that how PowerPoint works. It's not the right level of description. It is the right level of description for understanding maybe the instruction set, but not for understanding algorithms for linear programming or sorting. It's a different level of description. It's not clear what the right level of description is for understanding the processes like recognizing your mother, your grandmother, or other things that we do. So there are some people who think this is the wrong way to look, wrong place to look. Okay. Do you want to philosophize? Comments? Observations? Please.
So given an architecture, for example, PowerPoint, given an architecture, we can think higher level concepts about it because we know how it can be implemented. But if we don't know the architecture, how can we talk about higher level things without, I mean, really knowing?
Right. Yeah. So you're arguing for understanding the architecture, understanding the neurons, and after that saying, okay, what kind of computations would typically emerge from that? I very much agree. I tried to dabble in this 20 years ago, and my thinking was that if we could understand this kind of neural computation to the point of understanding what are the basic computations that it performs easily. Well, it was kind of a thinking of a hard bias. You know, what can you do, or a soft bias? What can you do easily with this kind of stuff? What can you not do easily? So we know that von Neumann machines can do sorting easily, but we don't know that brains can do sorting easily. But if you can figure out what things can do easily, you can move to the next level up, next level of abstraction. So, okay, what can you do with these kind of subroutines or blocks? Yeah, I agree with that. Some people argue that this is too high of a level of description, that actually you have to go below, because the story I told you about neurons, it's an abstraction. The actual computation performed by a neuron is actually much more complicated. I mentioned that it receives an average of 10,000 different messages at different places in the cell. Some of them come in low, some of them come in high. There are actually people who devote their life to studying a single neuron and how it reacts to 10,000 different inputs. And they use differential equations to describe the state of the neuron, and they write papers and discover lots of interesting things about how neurons, what computational neurons actually do. I take all of this and simplify it to all it does is integrate input and make a decision about firing. Is this the right thing to do? I don't know. It's possible that the brain achieves what it achieves because neurons don't do exactly integration, they do something different, and that by simplifying and assuming that all they do is simple integration, when I say integration I mean just summation, weighted summation over the input. If I make that assumption that all that really you need to know is that they sum over the input, I may be throwing away the most important part. It may turn out that if neurons really did only that, they couldn't do anything interesting, anything useful. So what is the right level of abstraction? Are we throwing away too much detail? Or are we keeping around too much detail and we won't see the forest for the trees because we're not at the right level? So there are people convinced that every possible answer to this question. There are some creatures out there that have an amazingly small nervous system. I don't know if it's C. elegans. I think C. elegans is a tiny microscopic worm that's been studied heavily by biologists. And I think it has on the order of a couple dozen neurons. So they've and it's always the same number. I don't remember what it is. It's like 37 neurons. Every worm of this type has 37 neurons. And they're connected in a particular pattern. So it's hardwired, no learning. But it performs computation nonetheless. It's hardwired fixed computation, but it's interesting computation. It does interesting stuff. It tells it how to move or whatever it does. It tells it. There are people who study the connections between these 37 neurons and how one triggers the other and the third inhibits the fourth, and what the overall emerging computation is. And they don't make the assumption of the simplification that I made here. So we're really grasping in the dark. We're assuming some level of description. We're throwing away a lot of detail. We're keeping a lot of other detail, and we're hoping that we threw away the right details and kept the right details. So this is our inspiration. Now what are we going to do with it? We're going to build networks of these neurons. I'm going to try to make a distinction between real neurons, which is what I've been talking about until now, and the abstract entities that we're going to simulate. They're often called artificial neural networks, or ANN. So you might see that term around. Artificial neural networks, but often people just casually talk about neural networks, and they mean, if they're computer scientists, they mean artificial neural networks. If they're biologists, they mean the real thing. So an artificial neural network might consist of a lot of neurons connected together, and they may be connected in particular patterns. So you can think about it as a graph, And if there's a loop in the graph, it's called a recurrent neural network. And there may be a signal that goes on in circles and may change over time. More often we will deal with a graph structure that does not have loops in it, a directed graph. A directed graph is also called a feed-forward neural network. Neural network, and i.e. it's a directed graph. Directed graph means there's a beginning and there's an end, and neurons are all ranked by a partial order. So a typical beginning and end might be that the input comes in through here and it spreads, the input from the outside world comes in through here and it spreads out to some other, and there's a general spreading, and then you read the output here. So this is an input-output machine. Even more commonly, we will talk about layered feed-forward networks, where you can partition the neurons into layers, and the connections are typically go from one layer to the layer above it. So a layered neural network feed-forward neural network would have an input layer and then some number of intermediate layers of neurons, and then a layer of output. So the last layer is considered the output. This is output. The first layer is considered the input. And the assumption is that neurons from this layer connect to the layer above it. Not necessarily every neuron to every other neuron. Sometimes they're fully connected. They will be called fully connected layered neural networks, but sometimes they'll be only partially connected. Now, is it not allowed to skip layers? It is allowed, but then it's not nicely layered. You can make any kind of topology you want, but a very common one that we discuss would be layered. Layered neural networks often fully connected. And then at the end there would be connections to here. I should make sure in the picture that every neuron, you can see that it typically gets input from many other neurons. And then it has output. The output goes to many others as well. What's the first question we want to ask about this kind of computational formalism? Representation power, thank you. It's the first thing you should ask. What can it compute? So this is a very difficult question. We're going to simplify it a lot. We're going to start with a single neuron. What can a single neuron compute? What kind of function mathematically can a single neuron compute? So I need to define for you more exactly what a single neuron is. I mean, a single artificial neuron. So here's a single artificial neuron. It has multiple inputs. Call them x1 through xn, and has an output. These are the obstructions of the synapses. You can call them synapses, you can call them weights, you can call them edges. We'll call them weights. So this is W1, W2 through Wn. Weights could be positive or negative. We're taking our inspiration from nature. Interestingly, there's a different mathematical reason why inhibitions are important. It is hard to do things with just excitatory connections. You do need inhibitions. We're going to make the assumption that at the heart of all neurons is a simple weighted summation of the input. What I called integration, but I didn't mean integration in the calculus sense. I meant simple weighted summation of the input. So we're going to write that as sum of wi xi. It goes from 1 to n. This is an operation at the heart of all neurons of all types. This thing is the total net input into this neuron. We'll call that net. I didn't tell you what the xi's are. They are inputs. Are they binary or are they continuous? They're typically going to be continuous numbers. Certainly in nature you can think of them either way. You can think of it as continuous, but you can also think about it as did it fire or did it not fire? Did this neuron fire connecting here or not? Our abstraction is going to be this is a continuous number. Sometimes we're going to talk about the restriction of this to the case where the inputs are binary. Most of the time they'll be continuous. The weights are always continuous. They're always continuous numbers, negative, positive. They could be zero, in which case it's the same as them not being there. So this is our net. Now what are we going to do with our net? I mentioned to you that the real neurons have something of a threshold function. They compare the total net input to some intrinsic threshold level, and if the total input exceeded the threshold level, they fire. If it didn't exceed it, they don't. I can draw that mathematically with a function here. Oopsie. That here says net, and here is the output. And there's some threshold value, let's say here. Threshold. And what would this kind of story look like? The story I just told you on biological neurons would look like this. First of all, the net could be positive or negative, right? Because these are positive or negative. So I have to start my drawing here. This is a picture of a threshold neuron. That's if you believe that, or if what you want to model is this all or none behavior. If you take a different time scale, not of looking every millisecond, but of looking over a period of a tenth of a second or even a second, you can think of the output of a neuron in the brain as a continuous variable that has a firing rate. Right? You can look at the average firing rate, you know, how many times it fired in the last tenth of a second or even the last second. If you do that, the output is continuous, and what would it look like as a function of the total net? It would look more maybe something like this. Straight line. In fact, I think the straight line might start here. But forget for a moment about the biology. We can decide ourselves whatever our function is that we'll implement, and we can make it any straight line. Or we can choose some other function. So the way we convert the total net into the output is called a transfer function. Okay? At least I call it a transfer function. I don't know if it's in the literature. I know I had white. Here. The transfer function, O for output, is the transfer function of the net. I use small sigma for the transfer function. We will deal with different transfer functions. So the common thing is that net is always defined the same way. What's different is in the transfer function. Sometimes we'll deal with a linear transfer function. We'll call this a linear unit. Other times we'll deal with a step transfer function. We call that a threshold unit. And other times still we will deal with neither this nor that, with some other transfer function. We should note that the transfer function has sort of built-in threshold. There's some kind of a threshold that's associated with each neuron. So if it's a threshold transfer function, we have to specify the numerical value of that threshold. If it's a linear transfer function, we have to specify the slope and intercept. So there's some parameters for the transfer function. Let's go back to our question of representation, and I'm going to simplify it even further for you. What kind of function can you represent with a single neuron that has a linear transfer function? If it's easier for you, you can think in space of 2 inputs or 3 inputs. Y equals mx plus b. How many inputs do you have here? Just one. I'm sorry? You have one input, and then you have 2 degrees of freedom, the m and the b. Okay. You can definitely implement that, but that would be a neuron that has a single input. What would it be for a neuron that has 2 inputs? Let's say x1 and x2. I'm sorry? So it'll be y equals w1 x1 plus w2 x2 plus a b. Right? So you have 3 degrees of freedom here. Did you guys take analytical geometry or in calculus? You know what these things are called? Louder, please. Surface. Yes, hyperplanes. Right? You familiar with that? Hyperplanes. Linear separators. These all mean the same thing. These are the answer to my question was pretty stupid. What can you compute with a linear neuron? The answer is a linear function. Linear functions. So if you have 10 neurons, you can compute linear functions of 10 continuous variables. Let me ask you a question. Can you calculate any linear? Can you implement any linear function of 10 continuous variables with a single linear neuron?
Can a neuron have negative output? Is that also?
Oh, absolutely. I mean, the abstract ones.
Right.
Yes. Please.
I'm going to go ahead and say yes.
Good. Thank you. Yes. Any linear function you can find because a linear function has to be expressed as having some coefficients, and these coefficients go directly to being the weights on a network. There's one thing that we didn't do the mapping of. Where did this come from? I'm sorry? Inside the neuron. Okay. Threshold. Is it the threshold? Is B the threshold? I'm sorry? I couldn't hear the first word. Invert the threshold value, is that what you're saying?
Built-in. It's built-in.
Built-in. This is the built-in threshold value, but in the negative. We usually think of thresholds as you take the full input and then you compare them to the threshold. Maybe you subtract the threshold from them, right? But here we have it in a plus. So B is actually the negative of the threshold. It's, strictly speaking, it's not a threshold because we're not dealing with the threshold unit. We're dealing with a linear unit. But it plays the role of the threshold. It's the free term. It's the intercept. It's the one that goes up and down. If you compare it to the threshold, it's with a negative sign. So plus B is like saying minus the threshold. Usually we use the word threshold when we have this kind of a function, a step function. Here it's a continuous linear function, but it's a similar number. Okay, so a single neuron that implements a linear transfer function effectively implements all linear functions. Any linear function, you can find a set of weights that will implement it, weight and threshold that will implement it. That's not very, that's very nice, but it's not necessarily very expressive. Most functions of interest are not linear. But it would have the advantage that because it's linear, it may be easier to learn. So we have this trade-off between hard bias and learnability. The hard bias is quite strong. It's only linear functions, which is not so good. Maybe it's too strong, but then learnability is good in this case. So let me see, should I tell you why it's good, or should we? Looking for one particular slide, but I'm not finding it. Okay. Okay. So I already gave you the end. I told you it's learnable, but let's discuss now how you can learn these weights. So suppose you want to learn a linear function from a bunch of training examples. So the training examples would be x1. So now I need two subscripts. One for which training example it is, and the other one for which of the x's it is, because I have x1 through xn. Which notation should I use? So x1 through xn, let's say this is x bar y1, x bar 2 y2, all the way through x bar m ym, where m is the number of training examples we have. X bar means it's an array of values, and x bar I consists of xi1 through xin. So the first index is the index into which training example it is, and the second index is the index into which input it is for this current training example. There are n inputs. It's a problem of mapping n inputs to one output, and there are m different training examples. You're given those m training examples, you're asked to find a single linear neuron that will implement it. How would you do that?
Well, you just invert it. I mean, it's a linear system. You compute the inverse of the matrix of the weights W, and as long as the examples are such that matrix is invertible, you've got one single answer.
Okay, so that is correct, and that is one way of doing it. That's called the algebraic method. You write down the requirements in algebraic form. The requirements are that the weight, what you're trying to find is the weight matrix and the threshold, or the weight vector and the threshold that will do the right thing on your input. So what does it mean do the right thing? So W times x1 bar should be equal plus b should be equal y1. W dot x2 bar plus b should be equal y2, etc. up to m. This is a system of m equations with n plus 1 unknowns. The n plus 1 unknowns are the n w's and the b. Okay? I should put a bar here too. This dot is what's called a dot product or an inner product. That means w1 times the first component plus w2 times the second component and so forth. You can write it in the matrix form. It would be, the w's would be the unknowns, w1, w2 through wn. And here you would have a matrix. Here you would have x11 through x1m, x21 through x2m, all the way through n, all the way through xm1 through xmn. You can take care of this b by adding it as the n plus 1 unknown and adding here an array of ones. And this should give you the y1 through ym. So it's a matrix of m by n plus 1, and this is a n plus 1 by 1, and this is a m by 1. So if you know linear algebra, you have a system. I didn't tell you the relationship between m and n. It may be over-specified, it may be under-specified, but if you have that and if there is a unique solution, you can invert the matrix and find it. You don't need to know the details of how you do it. If you took linear algebra, I hope you know it. But the point is, you could solve it that way. There are other ways you can solve it. There's a arguably simpler but computational way you can solve it. Anybody wants to suggest? Please. Okay, so it's not necessarily different than what he said. What you're saying is that even if there's no exact solution, you can find a solution that minimizes the distortion, right? So this is called the least square fit. You're trying to find a set of weights and threshold such that if you can't hit y exactly, you come as close to it as possible. So what you're trying to do is take the weight matrix times the input, subtract from it the y, and say you're trying to minimize this distance on average over all the training examples. So there are ways in linear algebra of doing that too, finding the least mean square solution. All this is algebra. There's a way you can do it that does not involve algebra at all. It's more AI-ish. And the way you can do it is by defining an error this way, and then numerically searching for a point that minimizes that error. How are we going to define the error? Just define it exactly this way. The error, so we're going to start with some value of the weights, any value, take it out of the hat. And when I say weights, I usually include in it the b or the threshold, which is negative b. Define the value of the weights, some value, and then of course this will not do the job. The output of the system will not be what we want it to be. But don't despair, we're going to calculate the difference between the output of the system and what we want it to be. We will call that our error. Okay? So we will define error, which is a function of the weights, as the sum of the errors of all the training examples. So I goes from 1 to m. Let me make the training examples be j. Okay? Just have a clear distinction. J goes from 1 to j. Now, what is the error of each individual training example? It is the y, the desired value, y sub j, minus the result of w dot xj. Right, this is this. and I'm going to square that. So I'm going to try to minimize the squared error. Why am I trying to minimize the squared error as opposed to just the absolute error or the error or anything else? Any ideas? Anybody else? Any ideas? Why choose squared error?
There could be positive or negative errors which would eventually sum into zero.
Okay.
But still it is the same.
That's a very good point. If I didn't do this at all, then some of the errors would be positive, some would be negative. Some of them would be overshooting, some of them would be undershooting, and they might cancel each other, and I don't want them to cancel each other. I don't want to take someone who's very accurate and someone who's sometimes 100 over, sometimes 100 under, and say they're the same. They're not. But I could still choose absolute value, right? I could put absolute value here, which will solve your problem. Why did I choose squared? Please?
It gives more of a weight to something that's really, really far off than to things that are closer, but not.
Okay, so it does imply a certain preference towards not having too big of deviations in any one case. If you compare two choices, you came up with one set of weights, you came up with another set of weights, your weights are wrong on one guy a lot, your weights are wrong on two guys half that amount. I prefer you. I prefer to be to spread my error over everybody as opposed to that's one way of thinking about it. So I penalize large deviations supralinearly, more than linearly. Being twice as wrong is more than twice as bad as being half as wrong. Okay? I don't have to do it with a square, I can do it with the power of 3 or 4 or 5. Why do I choose square? Please?
We want to actually look at the derivative of the function and see how it changes.
So that's a pragmatic consideration. Yes, I will soon look at the derivative, and derivative of square things are linear.
Continuous.
And I love linear things. So yeah, that is one good reason to choose a quadratic error function, is because the derivative of it is very easy to work with. There's another reason, deeper reason, which we'll talk in greater deal on. Squared error functions arise naturally in many situations where there is a Gaussian noise. Whenever the process you're modeling has Gaussian noise, the natural error function is quadratic. You don't have to understand why. You will understand why when we talk about it. So for that reason, and for the pragmatic reason, quadratic error is a very good thing to do. But you don't have to do it. There are other error measures you can use. You can use a logarithmic error measure, you can use an inverse, you can use all sorts of things. We're going to choose a quadratic one. So we have a square. And I'm even going to cheat and define it as half of this. Why am I doing that? It doesn't matter if I multiply my error measure by a constant, like half. I'm just changing my unit of measures from miles to kilometers. Why did I do it? For your reason, because when I take the derivative, this 2 and this 2 will cancel out. There's nothing deep about that half. So this is my definition of my error measure. I want to remind you that this W includes the threshold. In fact, to make it rigorous, I will redefine this B. Instead of calling it B, I will call it W0. So that when I write W bar, it includes W going from 0 to n, not just from 1 to n. A way to think about it with our neuron is to pretend that there was another synapse here called W0, and that it was connected to another neuron that always has the value 1. Okay? This is not what happens in nature. In nature there's no extra neuron that always is grounded to 1. In nature what happens is that there is a true threshold here. But mathematically, having the W0 connected to a neuron that is always 1 is the same as having a threshold of negative W0. So threshold equals negative W0. Incidentally, when people design circuits, they do use this solution very often. Those of you who know electronics know that you sometimes have sources of voltage that are grounded to specific values, and every time you need that value, you draw a line from there. So now that I did that, this W goes from 0 to n. And this is an exact definition of error. Now consider the space of all possible weights. What is the dimension of that space? Space of all possible weights. It's a Cartesian space. What is its dimension? N plus 1. It's an n plus 1 dimensional space. Every point in that space corresponds to one possible solution. Corresponds to a complete assignment of values to all the n plus 1 weights, from 0 to n. And inversely is also true. Any possible solution corresponds to a particular place in that space. And now our goal is to find the one place in that space, there may be more than one, but to find one of them where the error is 0. And if we cannot find, if there is no place in that space where the error is 0, we at least want to find the place with the minimum error. One other thing we should note is that the error function, it's a function of the weight, so it's a function of your location in space, is a continuous function of its inputs. Namely, if you make an infinitesimally small change in the weight space, you make an infinitesimally small change in your error, as defined here. And you can see the dependence on the input is through this thing. And these are all linear functions. This is a linear sum or inner product of two vectors. And then you subtract this from this, you take square. These are all continuous differentiable functions. So the overall error function is continuous in its inputs and differentiable. These are important properties. Whenever you have an error function that's continuous and differentiable, there's a way of minimizing it through a computational process we call gradient descent. It's a type of search. It's a heuristic search. Let me give you first an intuition of what it looks like. This beautiful picture from the book. It is very hard to visualize high dimensional spaces, so we always find ourselves giving examples from very low dimensional space. In a case here, this is an example where there's a single input, n equals 1. So the neuron has a single input. Single input means there are actually two unknowns, or 2 degrees of freedom. The weight along that input, which is W1, and the threshold, which is negative W0. Okay? So the error function, as written there, is now a function of 2 variables, W0 and W1. It's a continuous function in a 2-dimensional Euclidean space. So we use the 3rd dimension to measure the value of the function. It's a numeric value. So we're using 3 dimensions here to depict a numerical function of 2 variables. Okay? 2 variables are in x and y, and then z is used for the value of the function. And what you see is that the function does achieve a minimum somewhere. We can't see from here exactly where, but at some point, and that it curves up from that minimum. You also should know that the error function is never negative, right? Because it's a sum of quadratic terms. So it could be 0, could be, doesn't have to be, but it could reach 0, and then it curves up higher. And our goal is to find the lowest point, and hopefully it's a 0 point. But the way we're going to do it is we start with some arbitrary place. We start with some arbitrary place right here. So we start at this point, which happens to be W0 is a value of 1.8, and W1 has a value of negative 2.2, roughly. This point here. And we're in this point in weight space, means we have this much error. And we're going to somehow find our way along this curve down to the lowest possible point. And the way we're going to do it is by making local decisions on which way to go. we're going to, in a way, sense the slope of the space right where we are, and then take a step in the direction that maximizes the drop in that direction. So imagine yourself standing in a desert, in a hilly desert, in the dark. You can't see anything around you, but you can feel the ground underneath you with your feet. And all you do is kind of turn around and feel the ground in all directions. You can only feel the ground within like 1 foot of you. And you determine which is the direction of greatest decline, and you take a step in that direction. And then you feel the ground again. And you take a step in the direction of greatest descent, which may be the same direction, but maybe a slightly different direction. And you keep doing that until what? Until you got to the bottom or to a bottom. Until you got to a place where there is no way down anymore from where you are. Did you find the minimum of the entire desert? Not necessarily. You found the local minimum. Okay? So this is what gradient descent is all about. We'll talk about it again next time, and we'll move to more complicated nuance. Thank you.